All right, we're going to do a lot of Lewis dot structures, determine their Vesper shape, their angle, their polarity, and their intermolecular forces. So on the test, when you're doing these, you do not have to show process when you have to do all the Vesper and the stuff beyond it. You should still know how to do the process for each of these, but it's just too time consuming to show on the test. So we have hydrogen and fluoride. We're going to single bond them. And then I know that fluorine has 7 valence electrons. Okay? I know that fluorine and hydrogen are 2 different atoms, so they're going to have an unequal distribution of electrons, which you can kind of see. You know, hydrogen only has 1, 2 when you count his shared, and fluorine has a full octet. So we know it is going to be polar. Since it's polar, then we check. Is it an H and a fun bond? Yes, it is. It's an HF. So it's hydrogen bonding. So it's the strongest of the intermolecular forces. Okay, and Vesper shape, there's only 2 points. 2 points always has to be a line. So linear is always 180 degrees. Okay, so I have my Lewis dot structure, my Vesper, my angle, my polarity, and my IMF. Done. Okay, SCl2, or is it S carbon and 2 iodines? I actually don't know, so I'm going to do both of them here for you. Okay, so we have carbon with sulfur and 2 chlorines. Chlorines have 7 valence electrons. They make 8 with their single bond. Sulfur has 6, and he's going to want to do a double bond so that he can have 2, 4, 6, 8, 1, 2, 3, 4, 5, 6. Counting your valence and octets still important, okay? To make sure you have the right structure, because if you do this and then you don't show the extra electrons on chlorine or only show a single bond here, your entire structure is wrong. So your shape's wrong, your angle's wrong, your polarity's wrong, and your IMF's wrong. Don't do that to yourself. All right, so this is now a structure. Everybody has correct valence and is happy. Okay, and so I only look at the central atom. He has 1 atom, 2 atoms, 3 atoms, and no lone pairs, so he's a 3-0. When I look at my chart, that's a trigonal planar at 120 degrees. Okay. He is not symmetric because he has different outer atoms, so he is polar. Do we have any fun bonds? No, we do not. So it's dipole, dipole as your IMF. Okay, now if this was sulfur and chlorine, we know chlorines have 7 valence electrons, and they make 8 with their sharing of sulfur. Sulfur has 6 valence electrons, 1, 2, 3, 4, 5, 6. So that would be your structure if we were at sulfur dichloride. Oops, let me add a little, oh, I did have an L, it was hard to see there. All right, so we are good with the structure here. It meets valence and octet for all of them because it's not an ion. Okay. And we have 2 bonds and 2 lone pairs, so we have a 2-2, which is bent at 105 degrees. If it was water, it would have hydrogen bonding, and then your angle would be 104.5 because hydrogen bonding is stronger than regular dipoles. So those lone pairs push more. Okay. All right. CH2O, okay, carbon again in the center. He can make 4 bonds, so I know 2 of those bonds are with oxygen and 2 are with hydrogen. Oxygen has a total of 6. 1, 2, 3, 4, 5, 6. Carbon has its 4 bonds. Hydrogen has its single bonds. Again, I know I'm going super fast and not showing the process. You can always go back to the earlier videos to make sure you know how I got here. Okay, and that is a 1, 2, 3. So again, we're at trigonal planar. Remember, when you're using Vesper, it does not matter if it's single, double, or triple bond. You're counting how many atoms it's bonded to. 1, 2, 3 atoms. Trigonal planar, 120 degrees. Unequal sharing of electrons. Oxygen has a whole different set than hydrogen and different atoms. Okay, so we know it's polar. Is there any fun bonds? No. There is H and O in the structure, but not H and O bonded together in the structure. So dipole, dipole. Hey, CCl4, carbon in the center, chlorine I'm going to spread around. Carbon is in the center because he has 4 gaps. Chlorines, I got to make sure I have my 7 valence electrons. If you do not show these unbonded electrons, whole structure is wrong. Okay. He is a 4-0 because there's no lone pairs on carbon. Okay. And so he is tetrahedral at 109 degrees. He is symmetric, same outer electrons. So even though there's an electronegativity difference here, they are all canceling out. So even if you have a change here, it would balance with this guy, which balance with that guy, which would balance that guy. So this guy ends up being nonpolar. Okay. And that means that he works on dispersion forces. Okay, what else did I have to show? Vesper, angle, polarity, IMF. All right, we are good. Ammonia, make sure you remember that this is ammonia. Okay, not ammonium. Ammonium is pandemonium and it has more H's. Okay. So nitrogen's in the center because it has the most gaps, and hydrogen can only do a single bond. Nitrogen has 5 valence electrons, so I have that lone pair there. 3-1. Trigonal pyramidal. I'm going to go ahead. I don't ever remember what the angle for this guy. 3-1 trigonal pyramidal 107 according to your chart. When you use the internet, these numbers are all different because different people take the averages. So like, you know that 2,2 bent is 105, but there are some structures that are 106. Water is 104 because of the hydrogen bonding. So some of these tables that you look at on the internet are going to have different numbers than here. These are the IB numbers, so these are the numbers we use in class. Do not just Google what is the angle, because then if it doesn't match the chart we're using in class, it's wrong. Okay, and 107 degrees. Right, what else did I need? Oh, polarity. Okay, so we have all the same outer atoms, but we have a lone pair. So that means it's polar because of lone pairs. Okay, lone pairs push more than just hydrogen. And dispersion forces. Do I have fun? Yes, I do. So hydrogen bonding. So the strongest of the dispersion forces. PBr3. I'm going to spread around my BRs. Okay. And phosphorus has 5 valence electrons, so I know he's also going to have a lone pair. What's different about this guy? Make sure that you're putting in all the valence electrons so that you don't get marked wrong. Google does not put in these. Doesn't mean you don't need them. Okay, 3-1, still trigonal planar, 107 degrees. So these structures are very, very similar. Why is that? Because nitrogen and phosphorus are in the same group, so they tend to have similar bonding. Hydrogens can have a single bond, bromines can have single bonds. Again, typical and similar bonding. Just bromine has a full octet, where hydrogen has an incomplete octet. Polarity here is also different. We know it's polar because of the lone pairs, okay, but there's no fun bonds, so it's dipole-dipole. So this guy has stronger bonding than PBr3, even though they have a lot of other similarities. H2Se. Se has to be in the center. Hydrogen's going to be on the outside. When I go find Se, I see that he has 6 valence electrons. 1, 2, 3, 4, 5, 6. 2, 2 bent. 105 degrees. He has lone pairs, so he is polar. No fun bonds, so he is dipole-dipole. Last guy here, C2H2. Okay, central atom. Carbons are going to share the central atom because they both do 4 bonds. So you still do a bond in between, and then you spread the hydrogens around. C2H6 would be 3 on each side. By having those 3 on each side, each carbon has 4 bonds, so they're happy. No lone pairs or anything else happening there. We know hydrocarbons, If it's all C's and H's, it's nonpolar, regardless of what's happening. Okay, because of how it works out. Hydrocarbons are nonpolar. Okay? And this is just a single bond in there because 4 bonds. Oh, structure. Structure's weird, remember. Kind of split this guy in half. Okay, and then you can see this guy's a 4-0 and that guy's a 4-0. So you can either say 4-0 tetrahedral, 109 degrees, or if we're getting into a longer chain, you could just look at it overall, and it's like a linear 180. So for your year, I would take either one of those as the answer when we're talking about hydrocarbons. Nonpolar means what? Dispersion forces. Okay, and the longer the chain, the higher the amount of dispersion forces.